So, welcome to the 8th lecture. So today we will have a little bit of more fun with quantum optics. So, so far during previous lecture, we learned what is going on with the statistic, how to do the calculation in different representation. Essentially, I mean, going either with symmetric, normal order, or anti-normal. And today, at the end of the lecture, you'll understand why I was so emphasizing on learning how to work with this distribution, because when it comes to finding expectation value of certain operators, you need to understand if the operator is anti-order or normal order or symmetric. So then you have to go with either of those representations. And I think, if I'm not wrong, briefly we also discussed about the Beamspeaker action. And then we went with specific cases. So one of those cases was what I called Hongu-Mandel, or if I want to be precise, I have to say two-photon interference, and which people, they call it Hongu-Mandel rarity, or Ferren-Loden effect. And as I said to you, this year we wrote a review paper which appears in Progress in Report in Physics, which if you report on Progress in Physics, which if you want to know more, I will send you the manuscript, which you can read it and see different applications of it. By the way, also we will be discussing just a few cases when Hongu-Mandel will be useful in quantum optics. And then I gave you a couple of other examples. So what's going on with action of a coherent state? I think one of you asked this question. I think if I'm not wrong, was Eric, that he asked this question, that what's going on with the classical regime. And I showed that in the classical regime, essentially what is happening with the Beamspeaker will be just creating a product of two coherent states, which each of them, they have certain amplitude and a phase, of course. And also I gave you another example, which I think it's very important. I don't know if whether you had time to look into that, but if you don't, or you didn't, then we will go through it together. So let's review a little bit the action of Beamspeaker. Why I'm spending time on Beamspeaker? Because it's extremely important in quantum optics. Anyone that working in an optics laboratory, they need to work with Beamspeaker. And after Beamspeaker, I will drive also some other, let's say, other optical elements in the laboratory. And at most, final step, I will build up Mach-Zehnder interferometer. How is the action of a Mach-Zehnder interferometer in quantum optics? So let's go with the Beamspeaker action. Thank you, Felix, for sending me the notation. I think it is important to understand what was the definition of Beamspeaker. Usually I go with this way. So we have an input which is A and B. Then we do have C and D. Guys, correct me if I have a different notation. So then we say that C and D, they were linked to the input one via Beamspeaker action, which this Beamspeaker action, we set the phase such a way that it will be, we found the relation. It was TIR IRT. Let's just briefly check. So C will have a reflected part from B, which is true, and transmitted part from A. Excellent. And then we say that easily you can go, you can inverse this matrix. So then you can link A and B to the input one, which is output, which is C and D. And then from here we got that. Yes. Is there any mistake? No, okay. So A is equal to T C minus I R D, and B was minus I R C plus T D. Okay. And then we say that in quantum optics language, essentially these electric fields, they are linked to each other. So we can go with creation and annihilation operator. Then that is essentially A operator is linked to T, C operator minus I, R, D operator, and B is minus I, R, C plus T, D operator. And of course, we know what's going on with the creation operator, which is complex conjugate of that. So you will have T, C dagger plus I, R, D dagger, as well as B dagger is equal to I, R, C dagger. No one Chandler, okay, admit to the group, plus T, D dagger. Okay, so we find creation and annihilation operator of output in terms of the input one, okay? And we solve a few examples. So one of the example which was important, we look into the case when we have one single photon, and what we got the superposition of being in the mode of C and D. This is what we call that is a superposition, right? And we say that some people they call these single photon entangled, and I say that you have to be very careful because that's not entangled. Is essentially this concept. In order to have entanglement, you need two parties, two non-local essentially situations. And we say that if we want to create an entangled system from this single photon, it is good to have two atoms located in the port of C and D. And then if you look at the atom, let's say the total state, then you will find that the two atoms of C and D, they are correlated to each other. One is either in the excited state, the other one in the ground state, or vice versa. So this is what we call it entangled. So essentially you can use that to create an entangled state. And the other example that we looked into was Hungu-Mandel effect, which we just briefly discussed. So let's review that a little bit because there is an important concept which later on next lecture, we will discuss about that specific case. So assuming that you have one photon in the mode of A and one photon in the mode of B. So this is essentially what we deal with. And then we say that this is going to be a creation operator and a creation operator of B acting on vacuum. And then we say that if you use a Beamspeaker action, essentially what we will get at the end, we will get 1 divided by square root of 2. I think there is an I factor, right? For a 50-50 Beamspeaker, by the way. Let's just go with a specific case. Someone can correct me if I'm writing in the wrong way. But let me see if A dagger, C dagger, they are connected. Yes, I think is I. Then we have 0, 2 photon in B. Oh, let's go other way. 2 photon in mode of A, 0 photon in mode of B, plus 0 photon in mode of A and 2 photons in the mode of B. All right, have I done correctly or there is minus sign missing? Based on the definition that we had last time. Oh, let's do it. Doesn't matter. I think I'm sure that is correct, but let's do that properly. So then A is replaced by T, C dagger plus I, R, D dagger. multiplied by IR C dagger plus T D dagger acting on vacuum. Then what we do have is IRT C dagger power of 2. Then we do have plus T squared C dagger D dagger minus R square C dagger power of C dagger D dagger, or let's write it properly. D dagger C dagger, doesn't matter. In this case, minus plus I R T D dagger square acting on vacuum. And then what we got IRT, 2 photons in C and 0 photon in D, plus T square square root 2, 1 photon in C and 1 photon in D, plus minus R square, 1 photon in C and 1 photon in D, plus IRT square root of 2, 0 and 2 photon in D. Okay. So essentially, and remember that reflectivity and transmittivity of beam splitter was given by R and T, okay, square, of course. Remember, R and T, they are amplitude of Fresnel coefficient, okay? Essentially, from unitarity, we know that T squared plus R squared is equal to 1. In some book, they call them T capital plus R capital equal to 1, okay? So just get familiar with the notation. Maybe if you could go to some books like Loden book or Hecht, you will find that it's written this way. Anyway, for a 50-50 beam splitter, what you will end up with this case. So essentially, if you look at the situation, you will get 2 photons here, right? Which, if I want to write the photonic, let's say, state after the beam splitter, that will be the situation which I showed to you last time. Either you have 2 photons in C. Some books also, they show it in this way. 2 photons in in C and D, 2 photons in C and D, and finally you have 2 photons only in the port of D. Okay, but if you pay attention to coefficients of them and explicitly to the sign of the 2, what you will find out that the sign here is negative and the sign here is positive. And for a non-perfect beam splitter, or let's say a perfect beam splitter which is not symmetric, which has a certain reflectivity and transmittivity, then what you will see, you will end up with a state which is given by T squared minus R squared, all right, times 1 photon in C and 1 photon in D. Okay? Even this is one way that you can find out if whether your beam splitter is acting perfectly or it has some deficiencies. So then for a 50-50 beam splitter, that should go to be 0. Okay? So essentially, if I have such a beam splitter and having two photons coming in, all of those beam splitters, they were beam splitters for theoreticians, not for experimentalists. Okay. Okay, so if you have this beam splitter and you have two photons coming in, photon 1 and photon 2, essentially people, how they do the experiment, they have two detectors here, one here and one here. They call them detector of C and detector of B. And then these two detectors, what they do, they create electronic signals, okay? So we will discuss briefly what's going on with the action of detectors, but for the time being, what you will see that each of those detectors, when they receive a photon, what they do, they produce an electric current, and this current is a certain shape pulse. So with electronics, proper electronics, what you do, you create for each of those photons, you will create a pulse of electric signal, okay? And this pulse has a certain weight, and this weight is about few tenths of nanoseconds. So sometimes about 40 nanoseconds, sometimes even can be shorter depending on the quality of your detector. So if you look at the detector C and detector D, essentially, what you will get upon the time, these detectors, they will click, maybe completely in a random fashion. Okay, and also here the same scenario. This is what happens with time. And when you look at the time scale, that is, remember that each detectors, when they get a photon, they will produce a signal, right, with electronics, but then they are dead until they will recharge and they will function. They call this period, if you really want to look at it, is a avalanche effect. Essentially, what you will get if you, without processing of electronics, you will get a rising time, very sharp, and then it decays like that. But with electronics, we will process them and we will create certain, let's say, signal, which the signal is 5 volt, okay, and the shape is almost look like a rectangular. Anyway, so what is happening? Usually you have a dead time, and that is essentially, if you look at the time scale, maybe this is 40 nanoseconds, but then you have, let's say, you are watching that in 1 microsecond. You look at the entire the situation, entire the scenario in 1 microsecond, which is 10 power of minus 6 seconds. Okay. Then with electronics again, what you can do, you can ask yourself, hey, can I look at the time when the two detectors, they click at the same time? This is a valid question. The detector number, the detector C and detector D, they clicked at the same time. Where or when these two detectors clicked at the same time. We call these coincidences, okay? Coincidences. Okay, in order to do so, you have to look at certain time window, because those are pulses, right? You do have them, but you may say, hey, I am looking only at those cases where I discretize everything here. So I have, let's say, 2 nanoseconds, another 2 nanoseconds close to that one, another 2 nanoseconds close to that one, and etc. Right? So you discretize this whole scenario. And then you ask yourself, when in each of these 2 nanoseconds interval, 2 signals exist. This is what people, they do usually, okay? So, in order to find the coincidence or the coincidences, we need to look into certain intervals. So if the time is, let's say, 1 microsecond that you are watching that, you divide 1 microsecond into 2 nanoseconds, and then you will get a certain, let's say, discrete quantities, which I don't know, this can be 500 intervals. Correct me if I'm wrong. So essentially, you have 500 intervals. And now you look at those intervals and you will see that what is happening. The first interval, you don't get any signals here, right? Here, there is no signal, no coincidences. Here, no signals, no coincidences. Here, no signals, no coincidences, etc. No coincidence, no coincidences, no coincidences. Here is very at the edge, so you don't see any coincidence again, right? Because there is not in the same time window. When you go to here, you will see the coincidence exactly here. So you have one coincidence for that certain given time. And you follow up again with all, then you will have another coincidence here. Then you go and you don't see anything. At the end, you will end up maybe with 100 coincidences. Okay, so can someone tell me what is 2 nanosecond interval in terms of photon propagating in the free space? Do you know what I mean? In 2 nanoseconds, how long the photons will propagate?
60 centimeters.
60 centimeters, exactly. So what is happening essentially, what this time interval will tell me, that if I move these detectors, if I move these detectors by 60 seconds, 60 centimeters, nothing will happen. Nothing will change. I should be fine. I mean, essentially, the error is given by half of these. So essentially, I have to move it. Honestly, I have to move it by 30 seconds, 30 centimeters. So this is the interval that you do have it. Okay, that is dictated by the time interval that you are looking at the clicks of the 2 detectors. So if I move one of the detectors with respect to the other one by 30 centimeters, essentially nothing should change, right? Electronics, again, the same scenario. If you have a delay time here, or delay electronics, if you change it by, let's say, 1 nanoseconds, the situation should be similar. All right? So if you want to be very precise, then you have to reduce these to below nanoseconds. That doesn't need, I mean, because the frequency that we do have is extremely small, and what we call it accidental coincidences will be extremely low. So why I'm going to tell you this entire scenario. It is important to realize that what is happening here with entire of this is proper action of what? Beam splitter. This is nothing to do with detector. Okay? Detector is electronic. You can even delay it by, as I say, 30 centimeters. Nothing will change essentially, because for those people that they work in the laboratory, they know very well that, let's say Katie is working in the laboratory, I know. Felix is working in the lab. So what is the coincidence interval that you use for your experiment, Kate, for example?
I actually haven't done coincidence.
Oh, you have not done? Okay,
yeah,
cool.
no.
Interesting. Let me ask someone else. Who has done any experiment with coincidences? I think Flo did.
Yeah, I usually use like 5 nanoseconds.
Lovely. So
or 10 maximum.
So yeah, go ahead, Flo.
I have 7.
You have 7 nanoseconds. So usually in the real experiment, when you go to laboratory, what you deal with 5 nanosecond interval. You deal with 3 nanosecond interval. You deal with 7 nanosecond interval. Having a bigger interval has some defect. The defect will be noisier. Your result will be noisier, but essentially is totally fine with the experiment. You can always find a way to clean your data. Okay, so good. So this is the way that people they do the experiment. So they have 2 detectors. They and these 2 detectors, they will come to an electronic box. And this electronic box, what it does, they look at the interval of let's say those signals, and they look at them and they see if whether they can have coincidences. All right, good. So remember, this has nothing to do with beam splitter. This is just the detection technique. Many people, they do mistake and they believe that what happens at the detector. No, happens at the beam splitter. And essentially, if I want to be very careful, happens after the beam splitter, immediately at the exit of the beam splitter. All right, I will give you an example in order to understand the situation better. All right, good. So now what I do, I look at the 2 detectors, they click, and then I can record them based on what I highlighted with the yellow. All right, when the 2 detectors will click, what is the probability of this? When detector C and detector D click, what is the term that I have to highlight it in the yellow?
The T2 minus R2, the one that has a photon in C and another in D?
Exactly. This is the only case that contributes to both detectors at the same time. The other 2, which is this one and the first term, they contribute to one of the detectors only. The 2 photons will go either to detector C or to detector D. They don't go to both at the same time. So if you look at what we call it coincidences, only the middle terms, they will contribute, and the probability of these will be given by square modulus of this, which is T squared minus R squared, power of 2. All right? So this is what I say to you is T, essentially T minus R power of 2, or if I want to write it, because I know that, should we go with the transmittivity? Yes, let's go with the transmittivity. R plus T is equal to 1, therefore R is equal to 1 minus T. Then that will be equal to, have I done any mistake? 2T minus 1 power of 2. Good. So that is the probability of detecting the 2 photons at the 2 detectors. So essentially, if I look at the transmittivity, so I look at the probability versus the T, what is happening? This is probability of detecting both photons. With detector C and detector D. Transmittivity, when transmittivity is 1/2, that will be 0, clearly. when transmittivity is okay, you can plot it. So I mean, if when t is equal to 1 divided by 4, what you will get 2 multiplied by 1 divided by 4, which is 1/2 minus 1/2, so it goes to be 1/2. 3 divided by 4 multiplied by 1 divided by 4, sorry, multiplied by 2. 3 divided by 4 multiplied by 2, that will be 3 divided by 2 minus 1/2 will give me 1/2 again. So it will be like that. So that's 3 divided by 4, that is 1 divided by 4. Okay. Since it's a power of 2, it goes to be parabolic one. Okay. And the two cases, you can look at the situation that what's happening. All right. So that is the scenario that you do have for this case. Let's review the experiment, how people, they verify this experimentally. Okay. Of course, I mean, we have now a better feeling. Now we deal only with a 50-50 beam splitter. So essentially the outcome of that will be 1 divided by 2 square root of 2 with the I coefficient to 0 plus 0, 2. Okay. That is mode of C, mode D, mode C, mode D. So again, let's review the experiments. So photon is coming here. Photon in A and photon in B. What was the condition that you will see the Hongu-Mandel effect? Of course, we know that this is a 50-50 beam splitter. So what we are expecting, this. I don't want to go with really the full derivation, but I want to tell you something else. So Arman, you unmuted. Go ahead.
I was just going to say that they have to be indistinguishable.
Indistinguishable. Excellent. What do I mean by indistinguishability?
Let's say like the polarization has to be the same. Everything, all the degrees of freedom.
Lovely. Excellent. Everything should be identical, including arrival time. Right? So the two photons, essentially the two photons, they are not really localized. They have a certain distribution in the spatial mode, so in the longitudinal mode. So if I want to watch them, it's something like that. So usually you can create them with a femtosecond laser or even with CW laser, but that is what happens. So that's the photon that they are coming here. So the two photons, essentially, they should arrive exactly at the same time on the beam splitter. So arrival time can be considered as one parameter for indistinguishability. Okay, so the two photons must arrive at the same time. Okay, so if one is, assuming that one is delayed with respect to the other one, right? So the distance between these two, let's say I have a camera, I'm taking a snapshot of the photons. So I will see that this distance is about, let's say, in terms of space, maybe 200 micrometers. And that one is, let's say, 500 micrometers. And let's say the spatial coherency, I mean, in terms of length of the coherency, is something about 100 micrometer. And that one is 100 micrometer. Then what you will see, do you see the two photons arrive at the same time? No, because after 200 let's say when 200 femtosecond, roughly speaking, is passed, photon of A arrived to the beam splitter. So completely in the probabilistic way will be transmitted or reflected. While the photon A arrived at the beam splitter, still photon B is far away by another 300 femtoseconds. Clear, guys? So let's say after CT, okay, so it's after the time of 200 micrometer divided by C, then photon of A is here. And at that time, this is photon of A. At that time, photon of B is here, which is still 300 micrometer away. Okay, then beam splitter does its job. So the 50-50, it will be reflected, transmitted. So no coincidence. Coincidences will, if you look at the coincidences, still you will see the coincidences, because the same scenario will happen for the photon B after another 300 micrometer divided by C time. Okay, clear? So what people they do, usually they have a delay line. Which what they do, they control with the length of these, the arrival time of the photon. So this is what they control, its arrival time, which they call it trombone. Okay, so now what you do with controlling the arrival time, and you know very well that the two photons, everything about these two photons are identical, everything. Polarization, spatial mode, frequency, many things, everything is identical apart from the arrival time. Then what you do, you look at the coincidences, which again is given by the term of, let's say, going to detector C, detector D. Then if the arrival time is identical, you expect no coincidences. So it will be zero coincidence. If the arrival time is different, then suddenly you will see coincidence appears, either positive or negative. One is earlier, the other one is earlier, so with respect to each other, and then coincidence will appear. Okay, and so you know very well that the arrival time also can be translated in terms of frequency. So if you look at that one, I assume that is Gaussian profile for the frequency that I do have. Okay, I assume that this is a Gaussian profile for the photons. Clear? However, know that if you look at some of those papers and look at the Hongu-Mandel, what they call it, they call it Hongu-Mandel dip. And this is the visibility, that what we call it. And visibility is coincidence at maximum, coincidence at minimum. Different definitions they have, so they call it coincidence at maximum minus coincidence at minimum divided by a coincidence at maximum. Okay, this is one way of definition. Some people, they prefer to go with the standard definition, which is coincidence at maximum minus coincidence at minimum and divided by coincidence at maximum plus coincidence at minimum. So this is the more standard way, but people also, they use this definition. So
Sorry.
go ahead.
I don't get the definition of the coincidence parameter. Is it like the number of photons that reach the detector at the same time?
Now let's look at that. Okay, so how many people are there? Okay, good. So I think Nazanin, you are the person that you are asking the question. Okay, good. So this is the, do you see me? Yeah, right? Okay. So this is the definition of coincidence. With a certain rate, you are creating photon A and B. With a certain rate. Let's say in 1 second, you have 1,000 pair of photons. Okay? In a second, I will send 1,000 photons from A and B. Okay? Each one 1,000. And I'm sending to the beam splitter. Those photons, they're identical in any sense. Good? So they're identical. When they reach to the beam splitter, what is happening? They do bunching. Be careful with the bunching. This bunching is a bunching of Hongu-Mandel. They will stay together. They will exit from the same port, right? Either the two will be transmitted or the two will be, let's say, the two goes to detector C or the two goes to detector D, right? When this happens, there is no possibility that detector C and D, they will click at the same time. There is absolutely no possibility, because I'm assuming, by the way, I'm writing down here, I'm assuming that this is the detector, that photon A and B, they are coming here, right? I'm repeating this experiment 1,000 times, okay? So I'm sending 1,000 times per second. This is what we call the frequency of the experiment or ensemble that you do. Then if the two photons are identical, the two photons either they will go in this way or they will go in this way. So the two detectors, they will not click. Good? However, due to anything, maybe even wrong click, maybe the two detectors, sometimes they will click together. If they click together, you say that in 1 second, this clicked 1 time. I call it 1 Hertz coincidence. Maybe that happens 1,000 times. I call it 1,000 Hertz coincidence. Or what I call it, 1,000 coincidence in a second. Is it clear or still puzzle?
Yeah, that's clear. And also, we cannot determine how many photons the detector has detected, right?
This is a joke that usually I say to people. You are asking too much, Nazanin. No, no. I remember that I had a conversation with my supervisor, Enrico Santamato. So I was asking him many questions that how can we do that? How can we do that? Absolutely, this is a valid question. I mean, this is what we call it photon number resolving detectors. Photon number resolving detectors, they are extremely, extremely expensive and maybe not commercially available. Okay, only NIST is the institute that is producing that, with just 1 or 2 companies in the world. We take that, but it is a valid question. We cannot distinguish that, but let me give you another hint after that. Okay, I will give you how can we determine how many photons do we have there. Good.
Okay,
any other questions? I see Cicera is moving. No,
I've got a question for you, Ibrahim.
Kevin, yes, go ahead.
Yeah. If there's a photon number resolving detector, does that mean that we're not far away from getting like a proper single photon detector?
Single photon detector. We do have, I mean, we do have single photon detectors, but the detectors will not tell us that we have 1 photons or we have 2 photons or we have 10 photons. Whenever it receives.
Yeah, but
go ahead.
Yeah, so there's a that will tell us exactly how many photons we received, like within some level of accuracy.
Yes.
Cool.
Okay, so this is the scenario. I hope that you understand the situation better. Is there any other questions, guys? No? Okay. So the dip of Hongu-Mandel will tell you how good your two photons are identical. Okay? Because we know that everything is identical apart from just arrival time. If they were arrival time, they are different, then this is what happens. You will be in one of those two regimes. Either you will be here, or you will be here, or you will be somewhere else, or maybe you are just far away from that. And having an idea, what is this dimension, right? How good you could be close to, right? How far the two photons can be from each other. This is about something about 100, or let's say 200-300 micrometers. Okay, so for those people that they go to laboratory, really you have to be so precise. I remember that once that I built up Hongu-Mandel, what I have done, I mean, you have to work with fibers, you have to work with other things in the laboratory. I'm sure that most of you are experimentalists. I was in the site building at that time. So I went and I offered free coffee to 5 people. And I asked them to come to my laboratory and measure the distances, right? I give them a measure tape, and I asked them to measure the distances between, let's say, photon A and photon B, arrival to the beam splitter. And then I wrote down the numbers, and I look at the average of them, and I realized that I'm far by 5 centimeters. So I adjusted that. So one of the errors that usually you do have in laboratory is the systematic or the human error, which is based on your measurement. I mean, if you ask for many other observers to check, then you can reduce that. Good. So there is a measure on how is your two photon scenario good for doing quantum optics experiment, and that is dictated by the depth of the Hongu-Mandel. So this visibility will dictate if you can use your two photon states or two photon system for quantum optics or quantum photonics experiment. I don't recall well, but that should be higher than 73%. 50% is classical. Okay? 50% is classical. You can get it even from random sources. But 73%, something like that, 72 or 83, I don't remember really. Check it out in the books. That will guarantee that your experiment is purely quantum. All right. And if you look at experimental results, you don't see the dip like a Gaussian profile. What you see usually, you see something like that. Okay. So that is the visibility. You will see something like this. Okay. Anyone can explain to me? This is what you do see in the laboratory usually. Sounds strange, right? Because you see the coincidence has an, let's say, some certain threshold, but then it goes up just before the dip. Anyone?
Would it be from like some imperfection in the beam splitter? Like not being exactly 50-50?
No. You have done Hongu-Mandel because you use the Hongu-Mandel to do
Yep.
optimal quantum cloning attack to a secure channel, right?
Yep. Yeah.
Why this is happening? Anyone that can give me a hint will receive 1 mark.
Actually, I would like to guess. So, is that,
Tenglur.
yeah, I'm sorry, I'm late.
No worries.
Yeah, is that because of sometimes one detector will measure 2 photons at the same time?
Detectors, they cannot measure 2 photons. Sorry.
No, just guessing.
It is if they will be able to detect 2 photons, they will be what we call it photon number resolving detectors. We don't have them.
Okay, thank you.
Okay, of course. So anyone else? Manuel? Manuel is not there? Okay, I thought that he's somewhere. Okay, nothing.
Is it because your photons are so close together, like in time, that they both arrive almost like together at the same my God, sorry. They almost arrive together at the B splitter, but they're not overlapped enough to get to that that no coincidence area.
I mean, what you say is true, but nothing. It doesn't do that. I mean,
Okay.
Josh, anyone else? No.
Is it like detector dark counts or something?
No. I was hoping that you picked up. No, a detector dark counts. What it does, it just brings these, let's say, minimum up. This is the only thing it does. It's accidental coincidences. So usually, if you have a very good detectors in terms of dark counts, so if they have 50 dark count per second, so what you do, you say that this one is clicking randomly 50 times, this one is clicking 50 times, right? Then how is the possibility that these 50 from each of them, they will superimpose and produce the coincidence? So you multiply them by the time window. And the time window is 2 nanoseconds, usually is extremely small, so nothing happens.
Is this coming from 3 photons?
Nope.
I will give you a hint.
Is it because of the absorption?
Whom said?
Shisha.
No. I will give you a hint. Just take this, right, and inverse it. I mean, the upside down. What's that?
Gaussian?
I couldn't hear, sorry.
Think.
Is a sync. Who said that? No?
Me.
Okay.
Oh, phase matching.
Is what?
Is a phase matching problems?
No.
No.
Is
Sorry.
it
Yeah.
is it because the photon is only there for a finite amount of time? So it's the Fourier transform of a box plot?
A Fourier transform of, yes, a Fourier transform of something, but tell me. Flo,
The-
you were picking up. Eric, go ahead. Exactly. Eric.
I don't know, they had lots of names.
It is something like that, right? It's a Fourier transform of that. Good. What do we have in a laboratory which it has this shape? Usually, at the front of our detectors, we have filters, right? And these filters, what they do, they will pick up only a frequency of omega naught with delta omega, which the shape of the filter is a step function. All right? So the Fourier transform of a step function will be a sinc function. So essentially, if you look at those experiments, because we were discussing about experimental result in your laboratory or in papers, in the papers, usually what they have a bandpass filter at the front of detectors. And this bandpass filter has some sort of, let's say, step function. And if you look at, let's say, look at this, what detectors they will see certain frequencies it is what they call it post selections. And the spectrum that you have it is dictated by that. So you have to look at the autocorrelation between the two functions. This is essentially what happens here. Good. Now let's go to Nazanin's first question. So I think everything is clear about Hong-Gu Mandel, how you can do it in the laboratory, and what are the possibilities, and what are the results, and what is dictating the visibility of that. Good? Any questions? No? Good. So Kevin and Nazanin, they asked me about, and also Teng Lu, you also mentioned briefly about photon number resolving detector. Let's look at that. Let's see what do we mean by that. Photon number resolving detectors. So I have the beam splitter. Then the two photons arrive at the same time. Then the photon state is what we call it I divided by square root of 2, which is 2 photons, 0, plus 2, 0, and 2 photons at the C, D, C, D. So it means that, this means that I have C is here, so that's the detector. This is 2 photon state. And I have 2 photon states. Good. For a 50-50 beam splitter, what is the probability of each? It's given by the coefficient that you do have it here, right? It is 1/2 with the probability. This is probability. Being in that state, 1/2 being a probability of that state. Remember, this is a coherent superposition, is a state, is not a density matrix, right? So with a probability of 50 will be in either of those two cases. So now you asked me, guys, you asked me, how should I be sure that I have 2 photons there? True? Maybe my detectors are just, they don't work properly. Although it's strange that I'm changing a distance between, let's say, arrival time of 2 photons, and suddenly my detectors, they don't work. But someone may claim that, hey, maybe when you are moving the 2 beams together, you misalign them such a way that one of your detectors, they will not see it. Okay, you can claim that it might be due to the misalignment that you have it in your setup. Can you see my hands, guys? So it's look like that you move one of them such a way that the detector and the other side, it will not see it. Good. So now the question is that we have to prove to people that we do have the probability of increasing those photons to 50%. Previously, what we had, and if the 2 photons, they were distinguishable photons. When we have distinguishable photons, what is happening? You do have the probability of 2 photons going this way, 1 photon going up, 1 photon going down. Let's be precise, guys. I will label them with red and blue. Then I have the other probability, which is blue. And the final one, which is blue. Okay. Do you agree, guys, with that? Those are all 4 probabilities. What is the probability of each one happening? For example, let's ask Felix. Can you tell me what is the probability of the first one happening for 2 distinguishable photons?
For distinguishable, it will all be 1/4.
1/4. So it will be 1 divided by 4, this happens. 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 Remember, this is the probability, is not the coefficient. The coefficient will be 1 divided by square root of 2 of these. All right. And you have some I factor in the calculation, which we have previously done that. Good? Clear? Now I'm telling you, go ahead with your Hongu-Mandel famous experiment. Do it like this way. You have a trombone in one of the arms. You control the arrival time. And then you look at only one port, which is port of C. What is happening in the port of C? And I do see that we do have Hongu-Mandel dip. Okay, I mean, that's the coincidences. And now I'm looking at port C only. So again, let's go with someone who wants to be volunteer or voluntold. Thomas. Sorry, Thomas. Okay.
No worries.
So at the Hongu-Mandel dip, let's say here, at the port of C, what do we have?
We measured half
Of that state, right?
Yeah.
There we go. Excellent. So here we do have, with the probability of 50%, we do have this state, which is 2 photons coming out. Excellent. Good. Let's ask someone else. Josh, can you tell me what is happening here for the port C? It is not in the at the dip, so the 2 photons are completely distinguishable.
I don't know.
Look at the port C, right? Port C, you do have 2 photons here, right? So 25%, I have this state, right? And 50% of the time, I have this state. I don't care about the last one because last one has nothing to do with the port C, right? So 50% of the time, I do have this photon and this photon. Although they are distinguishable for me, it doesn't matter. Clear? Are you following? This is important, guys. So at the dip, what is happening at the dip of Hongu-Mandel, the 2 photons will be distinguishable. 50% of the time, you do have 2 photons coming in, okay? At distinguishable photons, what is happening? 50% of the time, you have 1 photon at the port of C, but you do have 2 photons at the port of C with 25% probability, okay? Let me write it down, just remember. So when distinguishable photon, I have 25% of the time 2 photons, or the 2 photon in the port C, right? When they are indistinguishable, that increased to 50% of the time. 2 photons in the port C. Clear? Huh, interesting. So now the probability of having 2 photons for the case that the 2 photons are indistinguishable has been increased from 25% to 50%. Can anyone propose me an experiment to check this. Did you get the question, guys? Now I have two photons coming out from the port C. And I know that in the case of indistinguishable photons, the probability is 50%, has been increased to 2 by a factor of 2 with respect to the case that they are distinguishable. How can I check that?
Could you put another beam splitter in after port C and then look at the coincidence rate of that?
Lovely, lovely. Exactly, that's the case. So what is happening if you have two photons here? And by the way, Thomas, I will give you 1 mark. I want to say that you will receive 1 mark, but you were too quick. So you have two photons, and if you put a second beam splitter after that, second beam splitter, what is happening is a Bernoulli distribution. Either photon, the two photons, let's say, because now it's completely random. So they can be either reflected or they can be transmitted. So what are the possibilities of these? The two photons will be reflected. The two photons will be transmitted. The two photons, one will be reflected, one will be transmitted, and etc. Okay? These are the 4 possibilities that it happens for that case. Then I will put another 2 detectors here. And I look at the coincidences between these two. So hereafter, everything is identical. Everything is identical for both scenarios, for these 2 scenarios. For both cases, you do have 2 photons coming in. So I will place 2 detectors there. What is happening due to the case that the 2 photons will go either, let's say, forward or go reflected, then I will get coincidences. However, the probability for the case of indistinguishable photons will increase by a factor of 2. When it increases by a factor of 2, then I will expect that the coincidences will increase for that cases. So this is what I can look for. So if I look at the time, arrival time, and I look at the coincidence at the second beam splitter, this is what happens. The coincidence is fixed because it's 25% probability, right? Essentially, it will be 50% of 25%. I don't care about the 50% because it's identical for both cases. Then suddenly, at the place that they are indistinguishable, that increase to 50 and goes down. And the height of these is twice of these. So if you go with an arbitrary unit, if you label that with the unit of number 1, or let's say unit 1, then that should be 2. We call these coalescence. So there is a way that you can check if whether you have really increased the number of photons there or it is just a misalignment. Okay, I will leave that. I think it was too much going through all of those details, but sometimes might be useful for you if you go to laboratory. There are different ways that you can check in laboratory and you don't get surprises. Questions? No? Okay. Let's go and build up a Mach-Zehnder interferometer now. Let's see what is happening. I want to teach you how to really use the formalism of quantum optics to build up a Mach-Zehnder for yourself. So I assume that there is no question. Good. So I have a beam splitter. For Mach Center, what I need? 2 beam splitters. I need 2 mirrors. And then I have 2 beams. One is going down, one is going up. So either beam goes up or beam goes down. So my Hilbert space is up and down. I assume that I'm working all of days. I don't have anything else. I don't have polarization state. If ideally polarization state, I will build up that as well. So we will do that in a few minutes as well. Maybe in 10 minutes, we will discuss about the polarization case. Clear, guys? So this is down state. This is up state. Cool? Good. Okay, so in short, let's call them up and down. So at the output of the beam splitter, what do you have? You have up prime, down prime, right? The beam goes down or the beam goes up, but there is a up prime and a down prime, or U prime and D prime. They will be linked to D and U. With what? With the beam splitter action that we just described. So that will be, let me write it down. So U prime, let's call it U1 and D1 is given by the beam splitter action on U and D. So let me check if U and D, they are the same way. U is transmitted and D will be reflected. Okay, so it's exactly the same scenario. It is transmitted, IR, IR transmitted. Okay, the same formalism that we had. What is the action of mirrors?
Isn't it
Reflect.
a phase, a pi over 2 phase?
Pi over 2 phase. That's all? It's someone else, I think, speaked up. Who was?
Change the K vector to
Change the K vector to. What do you mean? What is happening?
invert the K vector probably
So yes, but what
with some angle.
What it does. It can, I mean, the Hilbert space is defined, is up and down, what it does.
Oh, so it'll flip up to down.
Lovely. So what it does, if you have a U prime and D prime, they will bring it up to a U second and D second, right? So the action, this is the action of beam splitter. So beam splitter action, it is clear, is T, IR, IR, T. But now let's look at the action of mirror. Nazanin say that there is a pi divided by 2 phase jump. You are totally right. This is essentially what we had it for a beam splitter. So I will go with the sign of I, which is what it provides me. And Felix, you say that up becomes down. What is that operator? Because I have to write it in terms of operators, right?
Like 0, 1, 1, 0. I guess it's the X.
Can I
Or
write
the
it
Z,
in this way?
the Z probably. The Z.
Yeah. Can I write it in this way?
Yes.
It's true. Mirror action on the state of U prime, what it will be. Let's ask whom I ask almost everyone. Chandler, yes. Can you help me? So I have this operator of M, right? I'm acting U prime on the right side. What is happening? U prime and D prime, or U1 and D1, they are orthogonal to each other because they are bidimensional Hilbert space that we assume. So the product of these two will be 0. True? Then the product of these with that one, what will be?
The D2.
Yes, exactly. So that will be I D2. That is true, because if the beam going up, then mirror will be reflect the beams, and you will get I D2. And here, the same story. You will get I U2. Good. By the way, I can write entire of these in terms of matrices, which what Flick said, or in terms of Pauli matrices, which you will see it as well. It depends on you, really, what you want to do. Before doing so, let's do something crazy. Let's introduce a phase operator here. This phase operator introduce a phase of e power of I phi. What is the phase operator? Remember, this phase operator is, let's write it as a U because it's not photons phase operator. Can someone tell me what is the phase operator? Action. Manuel?
Just adds a phase.
To which one?
Wait.
Look at the figure, right? Which part of the beams will get the phase? Down part or up part? Do you see the yellow?
Yeah. I mean, if that's an element, I suppose the down part is getting
Exactly.
So,
yeah, it is essentially, you have to define where you want to place the phase. So if the phase is on the down part, then you have e power of I phi, right? What it does, it will not change up down. Nothing will happen with up down. The only thing is happening, it will take the down and add a phase to the down. So this will be the operator. I will help you. Is D1 plus U1. Nothing happens with U.
I have a question.
Go ahead.
We're not discussing the effect on polarization. We're supposing it's just an state.
We assume absolutely we don't care about the polarization for the time being. Okay. We will discuss polarization in completely different context, but similar to it will. The mathematics will be similar to this one. Okay.
Okay.
Because it's bidimensional. Clear? Guys, good, good. Excellent. So the phase is here. Can someone tell me what is the phase if I place it on the downside, upside? Anyone, please?
Well, you'll just get the upside back again. So it's just 1 multiplied by the up.
Lovely. Good. All right. Excellent. So what else do we have? We have mirror, we have beam splitter, we have phase elements. With these, we can build a Mach-Zehnder interferometer. That's all. So it's up to you if you want to write it in the terms of Pauli matrices, or if you wish to write it in terms of 2x2 matrices. Up to you. Which one do you prefer?
Aren't both the same?
Both are the same. Sometimes it's good to work with exponential, because if you deal with power matrices, then you work with the exponential term. But in terms of matrices, to understand, it's good in terms of understanding, right? Let's build up that. So you do have an input state, which is input state of, let's call it input, right? We go from left to right on the setup. And we will apply the actions that we do have. When you have an input state, we don't know what is the input state. It can be in coherent superposition of up and down, right? I have no clue at all. So what is the first element acting on? I go from left to right.
Beam splitter.
Beam splitter. So it will be beam splitter, the first action. After the beam splitter, what it acts?
Phase, if you have it.
Exactly, which is phase of on down or up?
Down.
Down, okay. Then
Mirrors.
mirrors, exactly. Then beam splitter. That will be your output beam. And that will give you the output of a Mach-Zehnder interferometer. Good. So entire of these can be labeled as U of Mach-Zehnder. Do you agree these are 2x2 matters? Clear. Lovely. So now I can go with what Felix mentioned for the mirror action, and I can go with what Josh and Manuel will tell me about the unitary action of, let's say, the phase element. So I know the beam splitter. The beam splitter is T-I-R-I-R-T. What about mirror? Felix, can you tell me?
I times 0, 1, 1, 0.
0, 1, 1, 0. Excellent. Merci. Josh, for U phase of down, yes.
Yeah, it'll be, it's going to be a diagonal matrix with e to the I phi on the second diagonal and a 1 on the first diagonal.
Is that fine?
Yeah.
Lovely. Okay. Do I have all elements? I think so. I do have all elements. Let's build up the unitary action of a Mach-Zehnder interferometer. It will be T IR IRT times mirror, which is I 0, 1, 1, 0, times a phase element, which is 1, 0, 0 e power of I phi. Then I do have also T IR IRT. Okay. Good. Let me do it with Mathematica. Someone can do that and can just, I don't know, if you have software, you can do that and just let me know. Someone is doing, or should I do? if you, I can share the screen, just what I'm doing with Mathematica, but it's up to you. If you can do the calculation, just let me know the end. Okay, so we found the value. And now let me share with you. So essentially for a 50-50 beam splitter, for a 50-50
Ibrahim, I think you have to reshare your iPad screen.
Oh, yes. Oh gosh, unbelievable. When your brain is tired and you want to do so many tasks at the same time. Working with Mathematica. Oh gosh. Okay, you should have it, right? Good. So what I have done, I mean, based on what you have seen with Mathematica, I made the phase to be symmetric. So the phase operator. So I introduced this one to be divided by 2 with respect to the other one, which is e power of minus I phi divided by 2. Okay. So, or you can say that I'm multiplying both sides by. I will factor out these phase. So it is e power of I phi divided by 2 with minus sign, and that is plus sign divided by 2. Then for the 50-50 beam splitter, U of Mach-Zehnder is given by this quantity minus cosine of phi divided by 2 minus sine of phi divided by 2 sine of phi divided by 2 minus cosine of phi divided by 2. Are you good? Excellent. Okay, so this is the action, the Mach-Zehnder interferometer action in the base of U and V. Oh, sorry, U and D. So U and D, they are, let's say, my vector space or my bidimensional Hilbert space. True? Good. Now, let's verify what I will get for some specific cases. So this is my Mach-Zehnder interferometer. It has an input, which is up and down. Sorry, this is down, this is up. And it has an output, which is up and down. Good. This is my machine. And the machine is unitary. And this is the action. Minus cosine of phi divided by 2, minus sine of phi divided by 2, sine of phi divided by 2, minus cosine of phi divided by 2. All right? Lovely. Oh, Cicero. Hey guys, you don't know. I have to really look at the screen and see if someone is entering to the room. I have to look at my Mathematica. I have to also do this calculation. So I'm really 4 tasks. Multitasking in this time. Good. So input state is related to the output by this Mach-Zehnder interferometer operator. Good. So let's ask someone who wants to be a volunteer. Gosh, let's go with someone. Can I create a qubit with that? The first question. I have a single photon. Can I build up a qubit with that? I'm sure that all of you know what is a qubit, because you are physics students or engineer working with proper program. Okay, so let's send one photon in the mode of up. So I'm sending with inside of this Mach-Zehnder interferometer, which has 2 inputs and 2 outputs. I'm sending one photon here. What I will get as an output? It will be cosine minus cosine of phi divided by 2 minus sine phi divided by 2 sine phi divided by 2 minus cosine of phi divided by 2 acting on 1, 0. This is the state that I have essentially. The outcome will be cosine of phi divided by 2 with a minus sign, then sine of phi divided by 2. What does it mean? Anyone wants to be a volunteer and tell me more?
We could tune any value we want for this depending on phi.
Yeah, but can you tell me in terms of output beam what I have? Output ports. This is up, this is down, right? What are the coefficient of these two?
Cosine and the sines.
Exactly.
The qubit.
Yeah, minus cosine of phi divided by 2 and sine of phi divided by 2. Remember, is a coherent superposition. It is not a mixed state. It is a coherent superposition. So what you will get, you will provide one up, or you go with up. Then after the Mach-Zehnder, what you will have minus cosine of phi divided by 2 up plus sine phi divided by 2 down. Ah, cool. I was able to create a qubit, right? This is what Felix and Manuel, they mentioned. With the phase, I can control the magnitude of the qubit, of the qubit. The amplitude of the 2 qubits. One qubit. This is the output. Is that the whole description of a qubit?
No, there needs to be a phase or a relative phase on one of the parts.
Exactly. And I will leave to Eric to make a Mach-Zehnder to act like any qubit generation.
We could stick another phase.
Where?
Phase plate. Right at the end.
Exactly. Right at the end, either on the down or on the upper side, you can stack a phase. Then what you will do, you can control the relative phases between the two modes. So let's build up that. Is it clear, or should I build it up, guys? Valerio, is it clear?
Yeah, it's clear.
Clear. Mahtab, I saw you, Tom. Okay. Josh?
I mean, I think it's clear.
Excellent. Thomas as well. So Arman, Kate, Kevin? Yeah. So adding just a phase element at the end will be clear. Tenglu? Sure? Good. Lovely. Okay. Excellent. So this is what we can do. So in order to have Henry, by the way, good. So in order to create a qubit, arbitrary qubits, what we need a beam splitter or 2 beam splitters. We need 2 mirrors. We need 2 phase elements, one here, one either in other ports or even at the beginning works. It's up to you. Let's do it in the output ports. So one at the phase. Then when you build up the Mach-Zehnder, this Mach Zehnder works for you as a machine which has 2 input and 2 outputs. And these 2 inputs and 2 outputs will provide you a qubit. Good? There is nothing strange with classical way, by the way. It's absolutely what you expect, also in the classical way. As an exercise, okay? Link creation and annihilation operator here to the input one. Okay? Do you know what I mean? I'm asking you exactly to build up what I have done for the Beamspeaker. For the 2 modes here, the 2 output modes, let's call them up of output and down of output. Okay? And here you have down of input, up of input. There is a link between U of output, or UO, let's call it, not University of Ottawa, but UO, and DO to U in and D in. Okay? This is what we build up right now. And now I am asking you to see if whether you can find annihilation and creation operator to be linked to each other, right? From the output to the input, and then tell me what is happening for this machine if I send a coherent state here. If I send the coherent state here, tell me what it will be the output. Good. Do you want me to do it for the coherent state and asking you to do it for thermal state or something else? I think Felix with the head is showing to me, yes, I have to do it for a coherent state, and then let's do it. I will leave it to you for other cases. Okay, let's do that. So the U action, essentially, as we described, since we found the phase, I will ask you kindly to agree with me that the phase action essentially, okay, I'm not considering that. Well, I can do that as well. Let's do that. Let me do a little bit of mathematical work, and then I will let you know. So up phase is down phase now. Down phase with dot with a phase of chi. Okay. I found it, but I don't want to do it for some other reasons, because it gets really very complicated in terms of math, in terms of having a phase factor always carrying with yourself. But let's do this for that case, right? When we found the Beamspeaker action. Here is no phase element, or I want to be careful, no second phase element. No second phase element. So essentially will be beam splitter, mirror, and a phase here, but nothing on the output. Okay, nothing really changes. It's just I don't want to carry exponential of I phi with myself always. I chi with myself. Just I'm doing that for this action. So it will be minus cosine of phi divided by 2 minus sine phi divided by 2. And that is sine of phi divided by 2 minus cosine of phi divided by 2. Okay. So now I will link U in D in to U out, D out. So what I have to do, I have to inverse these matrix. Minus cosine of phi divided by 2, minus sine phi divided by 2. Sine phi divided by 2 minus cosine of phi divided by 2, inverse. Okay, what is the inverse of that? Most of you definitely know. Simplify.
Transpose?
It is transpose, yeah. I just want to be sure because, okay. That will be minus cosine of phi divided by 2 minus sine phi divided by 2, sine phi divided by 2 minus cosine of phi divided by 2, acting on UO and DO. Good. So then U in is linked to minus cosine of phi divided by 2 UO plus sine phi divided by 2 DO. And then D in is equal to minus sine phi divided by 2 UO plus, minus cosine phi divided by 2 DO. Remember, this is the field, and essentially you can just go with operator formalism. Phi is real, then easily I can go for looking at the dagger operator. So U dagger in is minus cosine phi divided by 2 U dagger O plus sine phi divided by 2 D dagger O. I think you understand why I try to avoid the phase, because avoiding the phase, here you have to always take the conjugate of the phase and it messes up at the end. Di minus sine phi divided by 2 UO dagger minus cosine phi divided by 2 D dagger. Oh, all right. No mistakes? No? Okay, good. So what I want to enter to the to Marcender. Manuel, do you have a question? No? Okay. All is okay? Good. So I want to go for a coherent state. Coherent state inputs to the port. I can go as for 2 photons as well. It's up to you really, whatever you wish. Let's go with the coherent state. So we do have a coherent state, and the coherent state on the port of down. So coherent state at the port of down, what we do have, essentially, this is given by a displacement operator of e power of I, alpha A dagger minus alpha star A, is not A because it's a U port. So let's call it U in, is D in, D in, D in. Okay, acting on vacuum. Do you agree?
There's no I. for
Oh,
the
there's no I,
displacement
sorry,
operator.
of course, there's no I. My apologies. Thank you. So what I have to do, I have to just replace a DI and DI dagger with the operators that I have it here. So that will be e power of alpha. DI dagger is minus sine phi divided by 2 u dagger O minus cosine phi divided by 2 d dagger O minus alpha star d is minus sine phi divided by 2 uO minus cosine of phi divided by 2 do. Is all right, or I have done some missing signs, or etc. I think it's fine. Good. Remember that UO and DO, they commute with each other. They are independent. And that was also, we proved that for the case of Beamspeaker. So you can shovel them together, and what you will get e power of, let's have, I have to keep them together. Yes, these two together, e power of minus sine of phi divided by 2, okay, alpha u dagger O minus sine of phi divided by 2 alpha star, let's say alpha star UO. Since UO and DO, they are commuting with each other, I can write it as e power of minus cosine of phi divided by 2 alpha d dagger O minus cosine of phi divided by 2 alpha star do acting on vacuum. Then each of them, they are look like a displacement operator, but with the magnitude of minus sine phi divided by 2 alpha, and the other one minus cosine phi divided by 2 alpha. So the output will be minus sine phi divided by 2 alpha U tensor product of minus cosine phi divided by 2 alpha of D. Okay. Are you surprised? No. This is what I expect also from the classical light. Coherent state does this. So essentially, honestly, guys, I mean, this can be also a homework, but I want to really introduce this to you, that any complicated optical setups that you pass it to me, what I need to do, I just find out what are the optical elements action in terms of creation, finding either the matrix or finding the creation annihilation operator link between them. This is what you can do. And now you can also go for this case, which is, I leave it to you as an exercise. One photon in down and one photon in up. Okay, you send it to a Mach-Zehnder interferometer. Good. Do that at home. The result is very nice. Even you can get it here. I mean, it's just 2 minutes of calculation. So I will ask you to have a break of, let's say, I'm sorry, it took longer than I expected. Have a break of, let's say, 10 minutes, and then let's see each other at 4:41. Okay? I will pause. Let's wait for her. Oh, you are back. Good, excellent. Good. So I hope that you refresh your mind. Good. Good. So I have asked you to kindly looking into the case when you have one photon in the port A and one photon in the port D, U and U and D, and find out what it will be the output of Mach and the interferometer. Also, in the same time, would you please also check that 2 photons in D and 0 photon in U, and look at the Mach and the interferometer. This is interesting as well. This will be the basic for quantum computing with single photon or with photons. Okay. All right. Let's go for for more interesting case. So far, I just told you how to use optical operators. So let's say operators and design and see the action of specific setup. Do you like to learn another example? I mean, for example, polarization. Do you prefer to work also with polarization, or you can build up by yourself? Is it clear how to build up polarization basis as well, or is it not? It is not clear.
To me, at least, it's not clear.
Okay, so
Yeah, I'm going to follow Josh on that. Yeah, I'd love to see a polarization example.
okay, I will go with polarization as well, based on what Enrico told me. And again, I'm repeating, yeah, that's too much again, but I will do it with pleasure. Let's see how to build up that. So how many people are familiar with the polarization of light? I mean, in terms of manipulation. Just maybe use the signs that you do have it. Go with a thumbs up. Having an idea how many people they don't know. They just speak up. Okay. Okay. So then I will go with that. Maybe I was planning to have a coherency today, second order and first order coherency, but I can do it next week. Doesn't matter. What is important that you should learn the concept. So let's go. I mean, by the way, this is the basis that I built up for you. People, they call it pass Hilbert space. Okay. And as an example, you can build up N port to M port. Okay. You can do very complicated scenarios. So let me give you an example. This is not about Mach-Zehnder. This is about the pass in general, assuming that I have beam splitters. So now I can build up a very complicated setup, which you can go in. You can go in. Do you see what I'm going to do? It can be very complicated scenario. So you can build up whatever you wish. So, and essentially you may have N port in and N port out. Okay. And you can build up a quantum computer with this. This is happens, I think it was the beginning of this year, and it was a Nature paper, which people, they know for many years that, I mean, for 20 years, that how to build up a computer, a quantum computer based on photonic system. And what they need is just to implement them in the laboratory. It is extremely difficult to align all of them together, because you know that interferometers are very sensitive to vibration, and any small vibration will cause changes in the phase, and then you may not end up with the state that you wanted. But if you have a stable situation, you can build up this. Or the other way that someone can build up a quantum computer with photon will be having in-chip system. So you can have, let's say, 1 centimeter by 1 centimeter, but inside of a glass of pure silica, you can have waveguides, Beamspeaker, and all of those elements that you needed to implement. And then you can do that. So don't get scared about this scenario. What you need is just link what is the input to the output and build up the operators that you want. At the end, you know the action exactly as you wish, okay? So, but these states, they call them, remember, path states, okay? You work with many different scenarios. Let's go with polarization degrees of freedom. For polarization degrees of freedom, I will go with simple case. So I assume that you know what is the polarization of light and what is the birefringent. Let's review a little bit. So we know from the quantum optics as well and the classical optics that you do have two polarization of, let's say, HV, left, right, or A and D, or coherent superposition of them. It's completely up to you. So which basis do you prefer to work with? By the way, book by book also they have different notations, but you have to define your base, your Hilbert space. What do you want to work with? HV? Okay, let's go with HV. So this is the Hilbert space that I have is HV. So when I write this H, I mean that I have a creation operator of H acting on vacuum. Or this means that I have one photon in polarization of H. Good?
It's a dagger, right?
It should be dagger, yes, of course. Thank you. I can have superposition of these two. Which means that I have one photon in H, coherent superposition with one photon in V. Or I can write it alpha A dagger H plus beta A dagger V, acting on vacuum. Remember, when I deal with two photons, I'm emphasizing these guys. When you deal with two photons, you must be very careful, because these sort of notations can be extremely confusing. One example is when you have one photon in H, one photon is V. Okay? This formalism is misleading. Okay? You will see later on, I will give you an example why that can be misleading. But remember, when we have one photon in H, one photon in V, you have to define if the two photons, they have everything identical except the polarization. When everything identical except the polarization, then you are not allowed to write it in this way. You have to write it in the symmetric way because photons are bosons. Okay, you cannot assign it to that. If everything is identical, not only the polarization. Okay, we will discuss about that. But this is you have to handle it carefully. Okay. All right. Now let's go to the polarization. So when we have polarization, how can we manipulate polarization? Polarization manipulations. How can we manipulate polarization state? Someone is texting Kevin a lot. I can see from smile that you do have. Okay. Anyone giving me a hint? How can I manipulate polarization states?
Wave plate?
Yes. How? What does a wave plate? Who is familiar with wave plates? And who is not? I mean, essentially. Who is not familiar with wave plates? Okay, let's go with that. So wave plates are essentially some material which they have different refractive index. Refractive indices. So it means that if polarization of H is passing through, you will get a retardation. If polarization of V is passing through, you will get a different retardation. And the retardation is given by, let's say, gamma. So input and output, they are linked together. So output polarization is given by e power of I gamma divided by 2, 0, 0, e power of I gamma divided by 2 with a negative sign times input state. This is the action of a wave plate. All right. So okay, maybe I jumped a little bit fast. Let's say any material, the propagation of light in material is different from free space propagation by a refractive index. So essentially, when you propagate in air, you will get e power of I k dot r. And if you propagate inside of a material, then you will have e power of I, of course, the k, which is 2 pi divided by lambda. And then you have the thickness of material, and then you do have a refractive index of material. So this is depending on the polarization, and depends on the polarization. So for H polarization is a different value, for V polarization is a different value. So as a consequence, what happens when you go with H, you will see a phase. When you go with V, you will see a phase. What I'm doing, I'm taking out a global phase and I'm writing in a symmetric way. So gamma essentially is nothing than 2 pi divided by lambda, n of, let's say, ordinary minus n of extraordinary. Okay? Maybe divided by 2, I think, or twice of these. So this is what at times the thickness of the material. This is what I made it as symmetric way. Pay attention to the coefficient. I think that should be fine. Yeah, that should be fine. This is the action of a wave plate. All right. So let's call this wave plate of gamma. These wave plates look like this, guys. I don't know if I see myself. Yeah, it look like this. And if you rotate it, then the action will change. And we have to find that action as well. Now what we do, we assume that let's say the axis of these wave plates is aligned with H and V polarization, which is coming in. If the wave plate is rotated or the polarization is rotated, that will be a different action. Good. So this is for a wave plate which major and minor axis, or let's say ordinary and extraordinary axis, they are aligned with H and V polarization. So this is the axis of wave plates, like that, exactly aligned with the polarization. Good. How many wave plates do we have? Up to you. We can have any retardation. Gamma can be any value. Can be any value. But we know two specific gammas. We know two wave plates. We call them quarter wave plates and half wave plates. Good. Half wave plate means that the retardation is pi. So gamma in this notation is pi. Quarter wave plate means that the gamma is pi divided by 2. Okay. Then quarter wave plate, when it's oriented along x and y, then it is given by e power of I pi divided by 2, 0, 0, sorry, pi divided by 4. E power of minus I pi divided by 4. And half wave plate is given by e power of I pi divided by 2, 0, 0, e power of minus I pi divided by 2. You may see it in books. I mean, here, remember, I am missing a global phase of e power of I gamma divided by 2 with a negative sign. My notation doesn't have this global phase. Is important, is a U1 phase, but not for this sort of calculation that we are doing. Good. Remember, this action is an action of a wave plate which ordinary and extraordinary aligned with polarization of H and V, is not rotated. Now assume that your wave plate is rotated by angle of theta. So I want to watch it. So the previous case was like this. So I have a wave plate, which is, this is the axis of the wave plate. This is ordinary and extraordinary. Okay, and polarization of light, as we discussed, this is H and V. And now what I'm doing, I'm in the next case, what I'm doing, I'm rotating the axis by theta. How should I do the calculation and find the action of a half wave plate and a quarter wave plate?
You have to apply rotation matrices on either side of the operators.
Very close. Let me ask you in this way. Should be the same rotation?
No, it's going to be like rotation at theta on one side and then rotation at negative theta on the other side.
Exactly.
Yeah.
What I have to do now, this is rotated by theta. What I have to do, don't take note, please, and just pay attention to what I'm explaining because it's a little bit tricky. So now what I have to do, I know what is the action in the rotated base, right? In this one. But the problem is that my polarization is in this space. What I have to do, I have to rotate the polarization. So rotating the electric field by theta. Then when I do the rotation, I can go to what I call it lab frame of the crystal. I can apply the action of Whey Plates of gamma because this is the proper coordinate that I know the action. Then I have to bring it back after the propagation, of course. After I have to bring it back from the rotated coordinate to the lab coordinate, which is this one. Then I have to apply a minus rotation of theta. This is the electric field output.
I know it probably doesn't matter, but like in your diagram there, you rotated I think you might have rotated your electric field in the wrong direction.
It doesn't matter, honestly. It's up to you because the action of rotation is a different way. So yeah, doesn't matter. So what is important that the sequence is like that. Okay. Good. So I know the wave plate, which is e power of minus, gamma divided by 2 with positive sign, 0, 0, e power of minus I gamma divided by 2. Then rotation matrix is cosine of theta minus sine of theta, cosine of theta. Then I have the other one, which is cosine of theta, sine of theta, minus sine of theta, cosine of theta. All right. Then I have everything. The wave plate action at any angle of theta with a retardation of gamma now can be found as cosine of theta, sine of theta, minus sine of theta, cosine of theta, times the gamma and the other rotation. Good. Okay. Who has Mathematica right now? Open. Can you do that for, let's say, a half-wave plate at angle of alpha and a quarter-wave plate at angle of beta? And find this one, the matrix. So I'm doing also on my computer. Anyone got the result or not yet? So the matrix form for this, the entire of the situation will be e power of minus I gamma divided by 2 Oh, let's go with positive, and then cosine square of theta plus e power of minus I gamma divided by 2 sine square of theta, then minus I sine of gamma divided by 2 and sine of 2 theta, and that one will be minus I sine of gamma divided by 2 sine of 2 theta, e power of minus I gamma divided by 2 yes, cosine square of theta plus e power of I gamma divided by 2 sine square of theta. Okay, so that's the matrix, and now I can replace gamma by pi for a half-wave plate. For a half-wave plate, that will be with the I sign, cosine of 2 theta minus sine of 2 theta minus sine of 2 theta minus cosine of 2 theta. You should immediately understand what is this. Okay. And for a for a quarter wave plate, it is 1 plus I cosine of 2 theta. Oh, let me see what I can do that. Yes, I think I would prefer to write it in different form because it's beautiful. You can write it as identity matrix divided by square root of 2, 1, 0. Then I have plus I divided by square root of 2, yes. I can write it as cosine of 2 theta minus 2. 2, I can simplify that as also sine of 2 theta minus sine of 2 theta minus cosine of 2 theta. Okay. Good. No mistakes, no mistakes. Good. So this is the action of a half-wave plate as well. And oh, sorry. Let's replace alpha and beta instead of theta, guys. My bad. So I can write that as angle of theta and theta. Not necessarily they should be the same, but okay. Good. Excellent. So now let's do a little bit of fun. I have a single photon, one photon in H polarization, going to a half-wave plate, which is at angle of pi divided by 2. Tell me what is happening with that. So the action of a half-wave plate at angle of theta, you know very well. In general, it is I cosine of 2 theta minus sine of 2 theta minus sine of 2 theta cosine minus cosine of 2 theta. By the way, these should be known to you, right? Is it very similar to what? Do you remember these?
To a Mach Zehnder.
Yeah. Very similar to Mach Zehnder with a different phase, of course. So I'm sure that the action of a half-wave plate also will be similar to what I have it as a Mach Zehnder with a phase, of course. I mean, that can be resolved later on. So here you have annihilation and creation operator for H and V polarization, because this is your basis. Don't forget that. At the end, what you have to do, you have to connect H and V together, right? To the output as well. This was what I asked you from the beginning. So do you prefer to work in HV basis or left and right basis? In some bases, the action will be very simple. In some bases, they will be a little bit complicated. But at the end, the result is the same. So let's do that and see what we can get out of these. So essentially, AH, or let's say output, let's call it B. The output, I call it B. BH and BV, they will be linked to initial one, which is cosine of 2 theta minus sine of 2 theta minus sine of 2 theta, and then minus cosine of 2 theta. Then for input one, I have AH and AV. Now what I have to do, I have to inverse it. Let's see, I have AH, AV, and then I have to inverse these matrix. Anyone can tell me what's the... I think it should be to transpose. And the negative I will becomes, positive I becomes negative I. Can someone check that, or should I? I can do that as well. Yes, it's minus. Okay, take it away. Minus is plus, minus, minus, minus. Okay, good. Excellent. Yeah. So now I know that AH is given by minus I cosine of 2 theta BH minus sine of 2 theta BV. And AV is equal to plus I cosine, I sine of 2 theta BH plus I, there's an I as well here, cosine of 2 theta BV. And also I can find A dagger H is equal to minus plus I cosine of 2 theta B dagger H operator plus, sorry, minus I sine 2 theta BV dagger, and a dagger V is equal to minus I sine 2 theta of B dagger H minus I cosine of 2 theta B dagger V. Good. Now you can do whatever you wish. If the input beam is a coherent state, you know what is happening. If the input beam is 2 photons, you know what is happening, and etc. You can even cascade too many wave plates. So you can have a quarter wave plate at angle alpha and a half wave plate at angle beta. Okay? You can look at that. You can build up the action, and then you will understand the situation much better. Any questions? Good. So as the last example, I want to go back to beam splitter because there is something which people usually they don't talk about and is important to know, is the action of a non-perfect detector, which people in quantum optics simulated with a beam splitter. Okay, and I want to touch a little bit on this, and then I think all optical elements that you want to learn, you already have it in your hand, and you can, as a next time, I may ask you a task to build up a quantum computer for me to do a specific task. Okay. Now let's go to the action of beam splitter, or let's say having action of a non-perfect detector. Or even what I can say to you, a detector which is not photon number resolving detector. Non-photon number resolving detector. Okay. So detectors, they have specific quantum efficiency. And what do I mean by specific quantum efficiency? So if you have a detector, if you shine a photon on this, there is a probability the detector will produce you an electric current. Or what is happening essentially, all of those detectors, they are built up based on a photoelectric effect. So photon will be emitted and absorbed by the material, then one electron will be excited and goes to, let's say, conductive region, or you do have an avalanche effect, which will be cascaded that electron, and at the end you will have a pulse of electric signal. Okay, this is the scenario. It is good to get. It is easy to get detectors at visible range. It is a little bit difficult to get it at infrared range because they have a lower energy. We know that you have to really bring the electron from bound state to conducting one, and then you will produce that. You will produce the current. So that is essentially the scenario that you do have. And people, what they have, I mean, you are familiar with PMT concept or with avalanche photodetectors, which what you have, those electrons will be cascaded. One electron becomes 2 electrons, becomes 4 electrons, becomes 16, and it's becomes 16, and etc. So this is what happens at the end. However, all of those detectors, they are not perfect. So they cannot produce, they cannot absorb light with 100% efficiency. And this efficiency is dictated by, by the property of detector, acceptance, aperture of it, many other factors. We call this quantum efficiency of the detector. I will call it eta. Okay, and eta for good detectors can be close to 1. For bad detectors, is close to 0. Okay, so eta is a parameter between 1 and 0 for good detectors and bad detectors. By the way, getting eta close to 90% or 0.9 will cost you minimum $200 Okay, but having a range of, let's say, for, of course, depends on the wavelength, but let's say for visible, having a quantum efficiency around 70% is feasible. So you can buy a detector of 10,000. How people in quantum optics, in theoretical quantum optics, will simulate this? Because I mean, I have no clue how to simulate this situation. What we do usually, we say that I have a perfect detector. And a beam splitter. Beam splitter has the transmittivity of eta. Okay? So this beam splitter is refracted, let's say, Fresnel coefficient R is equal to square root of eta. Sorry, T is equal to square root of eta. And then R is equal to 1 minus square root of eta. Okay, so if you have, let's say, if you send one photon here, at the end here, what you have a coherent superposition of the two cases. Then the photons will be in superposition of being reflected on being transmitted. What is the coefficient of them? Square root of eta, 1 minus eta as a coefficient.
Should that be the square root of
Yes,
1
yes.
minus eta?
Yes, you are right. You are right. Thank you. So let's be safe. So R square is equal to 1 minus T square. And then it means that R is square root of 1 minus eta. Thank you. Thank you very much. Good. But remember that your detector is not resolving the number of photons. Okay? It doesn't have this capability. If it sees 1 photons, clicks, 2 photons, clicks, 3 photons, clicks, and etc. But 0 photons, no, it does. Good? Then, in order to simulate this and understand the photodetector, and let's say the detector action, let's look at the beam splitter essentially. Now your beam splitter is the object that does the work for you. So you are sending n photons in. Remember, the detector, it does not resolve how many photons do I get. Okay? I want to challenge myself, understands if I have a bad detector, or let's say a detector which has a certain quantum efficiencies, does it see 2 photons? Does it see 3 photons? Does it see 1 photon? Or the probability of all of them, they're identical? You know what I mean? The quantum efficiency of detectors is eta for detecting a single photon. Now you may have 3 photons. What is the quantum efficiency? You know what I mean? This is the challenge. That's the reason that we have to simulate it with the beam splitter. So I'm sending now n photons to that system, but I know that the system will get only that part, the transmitted part. Good. So again, I have to deal with the beam splitter. I have to again do the calculation for a beam splitter and find out what is the relation between the output, which is C and D here, with A and B. So essentially input beam, input state is n photon in A, which is essentially is A dagger power of n divided by square root of n factorial, right? and then I have vacuum. What I have to do, we have to link a dagger to the output. So I think we previously done this. So a dagger was now it becomes I. Was I or T? T. Sorry, it's T. T C dagger minus I R D dagger. True? I think it was something like that. Remember now T and R, they have to be replaced by eta, and R should be replaced by square root of 1 minus eta. Then output beam is T C dagger minus IR D dagger power of n acting on 0 divided by square root of n factorial. Good? Okay, what I have to do? I have to do the expansion. And remember, C and D, they will commute with each other, so I don't care really which one is first, which one is the last. So I can shovel them together, making them order or anti-order is up to you. It doesn't matter because they are commuting with each other. So the output state is given by summation of, let's do that, is binomial, is Bernoulli distribution, is K changing from 0 to n of choice of K out of n. Then I have T C dagger power of n minus IR D dagger power of, sorry, this is K, and that one will be n minus K divided by square root of n factorial acting on vacuum. So that can be simplified. I think this should change from 1, not from 0. Then it will be, that one will be simplified in factorial divided by K factorial n minus K factorial. K is changing until n. Then I have T power of K minus I R power of n minus K divided by square root of n factorial. And then I have C dagger power of K. I have D dagger power of n minus K acting on vacuum. Good? Okay. Then what we will get here is a summation over K until n. That will become n factorial, square root of n factorial. Then I have K factorial n minus K factorial. Then T power of K minus IR power of n minus K. Then C dagger acting a power of K acting on vacuum will give you K photon in the mode of C. Oh, let's write it somewhere else. K photon in the mode of C, and the other one will give you n minus K in the mode of D. And then from each one, you will have square root of K factorial, and from the other one, you have square root of n minus K factorial. Then doing the summation over K until n, you will get square root of n factorial divided by square root of k factorial, square root of n minus k factorial. And finally, t power of k minus I r power of n minus k. And then you have k photon in the mode of C and n minus k in the mode of D. Okay. So what is the probability of finding k photons?
I have a question.
Yes.
Isn't it simple to continue simplifying this, because you can see the shape of two coherent states?
How do I see the shape of coherent states?
For example, for the state K in C, you have some sort of alpha, let's call it like that, which is one of the coefficients. If you arrange it, and you can also split the sum, you get two coherent states, I think. Isn't it?
No, because in order to have two coherent states, you have to have two different sums.
Yeah, but
Here is one single sum.
you cannot split the sum?
No. Odd and even? No, it does not work. They are related together. This is a Bernoulli or binomial, essentially, if you want to call it, distribution. It look like essentially it look like having a coin, tossing it n times.
Yeah.
Is it like that, and then calculating what is the tail and face. That's all essentially. So what is the probability of finding k photons in C? This is what we are looking for, right? I don't care about D because the D will go here, right? D will be here. It will not be seen by the detector. I care only what are the photons that they will go to detector C, right? What is the probability of this? Is this power of 2, right? Essentially, because you can look at the inner product. I don't care about the port D. You can trace out on these. And then what you will get, the probability of k photons going there is n factorial divided by k factorial n minus k factorial, right? And then I have t power of 2 power of k, because I have to do the square modulus, and I know that k is real quantity. For minus I power of 2, that will be 1 essentially, and then the other one I'll get r power of 2 power of n minus k, and that is a probability of finding k photons in the port C. So let's write it in terms of eta. If you remember, t squared was equal to eta, and r squared was 1 minus eta, which is the quantum efficiency of our detectors. Then replace it here. The probability will be n factorial divided by k factorial n minus k factorial. Then eta power of k, 1 minus eta power of n minus k. Good? Oh, sorry, it's too late, I think, for you. I don't want to keep you. But remember, review this. There is a step which essentially is not bad, because after that, what I will do, I say that, look, I have n photons, and these n photons, if I send it to bad detectors, this is the probability of finding k photons on the detector, right? What is the n photon? It can be any values. So I have to sum over all n photons. So the total probability will be essentially summation of n factorial divided by k factorial n minus k factorial eta power of k 1 minus eta n minus k, and is changing from k to infinity because it's all n, then which each one having a certain distribution. Each of those photon numbers, which right now I deal with only with photon number of n, each of them, they have a probability of nn, okay? Did you get the point now? So I have an ensemble, of photon. It can be coherent, it can be non-coherent, it's up to you. Then we have done so far, we solve only for one Fock state of n, that will be the probability that you will get the photon there. And now what we are doing for all photon distribution of n, and we are summing over them with the probability of rho and n. And next lecture, I will start from this, and I will go to sub-Poissonian, super-Poissonian distribution, and I will find out the statistic which detector sees a photon, okay? I will stop here, and if you have questions, I'm here.